Here we discuss the vestigial sideband modulation. So in previous videos we have discussed the double sideband modulation and the single sideband modulation. So vestigial sideband is slightly different from those two, and it's more practically used in communication systems. Now, why do we need vestigial sideband? The reason is because it's difficult to generate an exact single sideband signal. They require that the message signal MT have a null around the DC. So near the zero frequency region, there should be no significant spectral component in the case if we want to generate an SSB signal, because if we use a filtering technique, then the filter needs to have a sharp cutoff near the zero frequency region. So then the other method of generating SSB was the phase shifter method. To get a perfect phase shifter is practically not realizable. So generation of DSB signal is much simpler, but it requires twice the signal bandwidth. So that's why SSB and DSB have these problems. Then we have the vestigial sideband modulation, VSB modulation. It's also called asymmetric sideband system. So it's a compromise between the two, DSB and SSB signal generation. Now, VSB, the vestigial sideband, inherits the advantages of DSB, double sideband, and single sideband, but tries to avoid their disadvantages, and there's a small cost, as we will see, that is in terms of the bandwidth. VSB signals are relatively easy to generate, so we are going to use similar technique as the DSB signal, and at the same time their bandwidth is only a little, like typically 25% greater than that of SSB. So the main benefit of SSB was the bandwidth conservation. VSB also provides the same benefit, but it has a slightly greater bandwidth, around 25% compared to the SSB. So in VSB, instead of rejecting one sideband completely, as we do it in the SSB, there is a gradual cutoff of this one of the sidebands, right? And so that is acceptable, as we will see, because we can still demodulate our signal completely. Baseband signal can be recovered exactly by synchronous detector in conjunction with an appropriate equalizer filter. So for just like the case of a double sideband, we need a synchronous detector. Along with the synchronous detector, we would need an equalizer filter, H not F, at the receiver. So if a carrier is transmitted along the VSB, then we can even demodulate the VSB signal using envelope or rectifier detector if the carrier is transmitted along the VSB signal. So if we look at the different modulation schemes graphically, if we look at their spectrum, so this is the signal MF, this is the spectrum of the signal, and then we have the double sideband modulation scheme where we can see both the sidebands exist around the carrier frequency. Then we have the single sideband where one of the sideband exists along the carrier, and then we have the VSB where we can see there is a small component of the rejected sideband as well in the signal. So that is because the filter that we are using at this point has a gradual cutoff, and practically filters have gradual cutoff. We cannot have a perfectly sharp cutoff filter. So how do we generate a VSB signal? So this is the expression for a VSB signal, and this is the block diagram. So we have the signal MT, whose Fourier transform, or the signal in the frequency domain, is represented by MF. We simply multiply it with the carrier as we do it in the DSB signal. At the output we use a filter HIF. So that means in the frequency domain the DSB signal, which is this one, is multiplied with a filter. So this is the filter that converts the DSP signal into a VSP signal. So remember this expression, we will use it later. Now, the VSP shaping filter HIF allows the transmission of one sideband but suppresses the other sideband, not completely but gradually. This makes it easy to realize such a filter, but the transmission bandwidth is now somewhat higher than that of SSB, as we discussed previously. It's typically around 25 to 33% higher than the SSB signals, right? Now, how do we demodulate this? So, this is the VSB signal that has been received at the receiver. So, we will look at the technique where synchronous demodulation is performed. So, for that, we need to have a carrier, a local oscillator that is multiplied with the received VSB signal, and at the output, we obtain the signal ET. This signal ET is represented by the expression shown here. So it's the product of the VSB signal and the local oscillator. If we take the Fourier transform of this combination, as we know from previous knowledge, that this will become equal to the what you call the frequency domain of the VSB signal that has been shifted by FC. So now the same VSB signal that we have received, it will have two sidebands, like one at F plus FC and the other one at F minus FC. So this is like frequency translation. So we know that if we multiply a carrier with a signal, so it translates, it shifts its frequency by the amount of the carrier, right? So this is the signal that we obtain at this point, right? So this is the, in other words, the Fourier transform of ET. Now you can see after this we use a filter H0F. We will see in the coming slides that this H0F is related to HIF, which was the filter at the transmitter side. What is the relation between them? We'll see in the coming slides. After this, the aim of using this filter H0F is to get our signal back, the MT that was transmitted at the transmitter. So signal ET is further passed through the low pass equalizer filter. So one thing is for sure, that this filter H0F must be a low pass filter, right? It's because we want to extract the low frequency signal MT, the message signal, which as we know is a low frequency signal, so it's a low pass signal. The output of the equalizer filter is required to be empty. Hence the output signal spectrum is given by now the MF that we obtain at the output of the H0F. The signal that we obtain at the output of H0F should be equal to MF, right, which is the transform of MT. So that means the signal that we have obtained before the equalizer filter is equal to this. After it's passed through the equalizer filter in the frequency domain, result is this, that they both are being multiplied. So this H0F should be chosen such that the output of this product is equal to the signal, the Fourier transform of the signal MT. So now if we substitute the values of the VSB signal phi VSB in this expression, and eliminating the spectra at the higher frequencies, because now at the receiver this VSB signal, which is already, it's a modulated signal, it's already at a higher frequency, it's again multiplied by the carrier, so that will shift it to even higher frequencies of plus FC and minus FC. So the total shift would be equal to plus minus 2 FC. So since one thing is for sure, this H0F must be a low pass filter, so these high frequency components are rejected, and this signal VSB is also shifted to low frequency signals, so it will have both the sidebands. So the high frequencies are suppressed by the low pass filter, so at the output we are left with MF, and so in this VSB signal we had the product of two terms. One was the MF and one was the HIF at the transmitter side. So this MF the higher frequency component of MF would be rejected. The low frequency component, which is MF, is left as it is. And then we have because we had HIF in this, we had the HIF component that is shifted to HIF plus FC and F minus FC due to multiplication at the receiver. And then finally we have our receiver filter H0F as it is. So from this expression, if we rearrange, you see we have MF here and MF here as well. So if we rearrange this, we get the expression for the filter at the receiver. So you can see that the filter at the receiver is the reciprocal of HIF plus FC and HIF minus FC. So here we can see, because HIF is a band pass filter, right? So but if we shift it because of multiplication at the receiver, so this will become a low pass signal because of F plus minus FC. So this whole represents a low pass signal, so that means H0F must also be a low pass signal. So from this we can see, depending upon the shape and characteristics of the filter at the transmitter, we have to choose the filter at the receiver to obtain our signal MF or MT in the time domain. So the low pass filter response H0F can be obtained from the band pass filter response HIF that was used at the transmitter side. So this was the discussion about how to generate and detect VSB signal. So now, where is this signal used? It's generally used in broadcast television. It's a VSB is a compromise between SSB and DSB, which makes it very attractive for television broadcast systems. Baseband video signal, the video signal for the television occupies a large bandwidth of 4.5 megahertz, and if we use DSP signal, this becomes 9 megahertz, twice of 4.5. So it would seem desirable to use SSB to conserve bandwidth, but doing so creates other problems. The problem is that in the video signal, we have a strong frequency content around the DC zero frequency, so that's why using a perfect sharp cutoff filter is not possible. So SSB is not a feasible option. So as a result, VSB is being used for the television broadcast, and there is a slight difference from what we saw previously. The filter HIF, instead of using one single filter at this point at the transmitter, its transfer function is divided into two parts. So at the transmitter we have HTF, and at the receiver we have HRF. So these two, when they are multiplied, they give us the signal, they give us the filter response HIF. Previously, we perform demodulation using the synchronous detection scheme, where the input VSB signal is multiplied by the carrier, and then we use H0F to obtain our signal MT at this point, right? So the response of H0F we know is represented by this signal, this function. So HI was a band pass filter. When we have shifted versions, then it becomes a low pass filter, and so H0F must be a low pass filter as well. So the spectral shapes of the VSB signal for broadcast television are shown here. So vestigial shaping filter HIF cuts off the lower sideband spectrum gradually. It starts at from 0.75 megahertz. So this point is 0.75 megahertz below the carrier frequency, and it completely suppresses the signal at FC minus 1.25, right? So if DSB spectrum was transmitted, then you can see we have this extra sideband, like extra bandwidth being transmitted. But for VSB, we can see we can save this amount of bandwidth. This is the video signal part, and this is the audio spectrum, audio signal part. So the audio signal is located at it's shifted at a frequency of 4.5 megahertz, because the bandwidth occupied by the video signal is around 4.5 megahertz. So after that bandwidth, we place the spectrum of the the audio signal, and we transmit it as it is. We transmit it as a DSB signal because the spectrum is not very large, and so we don't need to suppress this anymore. So I hope this was helpful in understanding the VSB signal. If you have any questions, feel free to ask in the comments section, and please don't forget to subscribe to the channel. Thank you.